Hi class, this is the Activity 6 video, and this is the new Activity 6, and I made a lot of adjustments and some changes to it, and I may even make a little bit more after I put the video out, but it won't be anything drastic. A few new links or um, just add a few things in, but we're going to go ahead and get started on this. This is about procedural generation and how that links in general to art and design, but more specifically to game design. And so that'll be kind of the applications. And it's been around for not like the golden ratio or something like that, where thousands of years, but people have been writing procedures on how to do things for a long time. But with the advent and development in computers in programming, then it kind of just seemed to all kind of mesh together. So the visual development fields seem to have lots of procedural generation. Uh, Not so overwhelming in gaming, but it's becoming more of an item than it had been in recent history. So but I just want to start out here, first of all. What do we mean by a procedure? And this, there we go. So it's a little slow working, but I'm not sure why. But okay, we'll work with it right there. Again, this is a definition, kind of what I'm uh, talking about when I say a procedure. So fixed, definitely a fixed step-by-step sequence of activities or course of actions with a definite start and end. So it must be followed in the same order to correctly perform a task. Repetitive procedures are called routines. Okay, so we have a procedure, uh, and then you could list three real life examples of where procedure is used. So again, you guys can make up. There's lots and lots and lots of examples. If you want to bake a cake, there's a certain procedure. You start maybe dumping the cake mix into a bowl, and then you add some eggs and some flour, something, butter and sugar, and mix it all up and bake it. And there's a procedure for baking cakes. Or if you're going to perform, a doctor's going to perform a operation, and they're going to do like an angioplasty, and they have a very systematic step-by-step procedure and how they start and go through the whole process and so on. And so you can list some examples of where we have these step-by-step processes to complete a task in anything, not just art or whatever, but in anything at all. And then in number 3, it says describe 3 examples where a procedure is used in creating art. And this first link, if I can get that to work, there we go. And again, it's kind of running slow here. And this is not it. Okay, so in this one, here's some, again, 10 artists and their process of creating art. And you can go down and look through these, and with some different artists, and they talk about in general kind of things. And you'll notice it's not so specific. It seems to be a lot more general things that they like to do when they get started. And you can kind of maybe read. Just some are more specific than others. Um, he said, I use a Wacom tablet to draw on. I make bold digital outlines traced from the digital painting, detailing important parts of the work, print that out, then use a projector, then to copy it onto the canvas, do bold outlines, make it easier to copy, and then if it's simple, you just so this is a listing of steps, and again, you can kind of take a look at those, and then again, there's another listing here of more famous artists and their art, creative processes, procedures, and how they develop something. So again, we'll keep moving on here. And so for classroom assignment 1, you're to write a procedure that you use to complete an artistic task. And so your procedure must have a minimum of 5 steps. So that should be easy for you to think about. How do you typically, and it may not be the exact same thing every time. It might not be even the exact starting point and the exact finishing point, but we're trying to think about this idea of procedural generation. So we're just trying to think about procedures first. And again, I'm going to move on with the video. You can stop it and work, however much you want on that. And I'm going to keep moving through this. Okay, so procedural generation, what is procedural generation in computing? And I'm going to try, this works better than the Google Chrome. The other one wasn't working very well. So this one's a little bit better. And in computing, procedural generation, method of creating data algorithmically. Okay, algorithmically. Now I have a video you can watch right after this link on algorithms and computing and so on. And it says here in math and computer science, an algorithm is a finite sequence of well-defined computer implementable instructions. So it's a procedure. It's like writing code, basically, is writing an algorithm, typically to solve a class of problems or perform a computation, and so on. So, all right, so procedural generation, we can create data algorithmically through a combination of human generated assets and algorithms coupled with computer generated randomness. So when we talk about that, this human generated assets and algorithms, and we almost think about fractals and stuff like that. We talked about how fractals have a structure to them, but they have a randomness involved too. And we talked about how, used in computer graphics, common in compute textures and 3D models and so on. So, and here's the video. This link, I'm not going to play it, but you should it's like 5 minutes, and you can take a look at it. And it's a good 5 minutes of talking about algorithms. It's kind of interesting, and it ties in with what we're talking about. So what is currently being what is it currently being used for in computer graphics and video game? Okay, procedural generation, this is referring to. And we just kind of talked a little bit about that, and writing algorithms to work with maybe texture and 3D imaging and so on. And it says, what are some of the advantages to procedural generation in computing? And I would say the most common things that people talk about is the saving space, and that's what initially it was used for in computing. We didn't have much space at all in computers, and so to do even the very simple video games, uh, it took up all the space, and so you almost had to try to write things with code without with formulas and so on, uh, for it to be able to work and run and speed, and um, so there's some definite advantages to it, and you can do things on the fly. You don't have to store as much, and so on. So number seven, why is procedural generation becoming a larger part of game development? But the typical thing here, this is just an interesting article. Again, three failings of procedurally generated game design. But let's first look at, it says a major evolution of game development over the years would have to be the use of procedural generation. Instead of having a linear experience that's one and done, you can create something that's always keeps the player guessing. Rogue was one of those games that used a lot of procedurally generated um, gameplay, and so survival simulator games have been using procedural generation to extend their replayability. When it works, you have a game with almost unlimited replayability. It's not perfect and can hurt as much as it helps. Okay, so again, we have some advantages here, and so there's interest in it. People are getting better at it. That's one of the other reasons too, and we'll talk about how that getting better at developed here in a minute with the math. Number eight, has procedural generation always been used in game creation? Yes. Okay, the answer to that is definitely yes. And what are three disadvantages? So let's pull that back up. We were looking at. So again, we're going to skip down here. Okay, limited foundation. And I'm not going to, you can look at this. I'm going to just kind of keep moving. So again, limited foundation, and got to be kept basic. And the harder it is to create something that makes use of all the stuff that you can, generate randomly. All right, so can't process uniqueness. So you take the procedural generation takes a lot of the creativity, the individual creativity of the game designers, and the idea of stuff that's mass produced versus handcrafted. And you can usually tell at this point, especially in the games that are out there, the ones that have come out recently, you can tell the difference in the ones that are more procedurally generated. Will it get better? I'm sure at some time, in the future, that they're going to continue to get better at this. So we're kind of really almost in an infancy stage with this in game design and so on. And but there's a lot of opportunity out there, right? There's not a lot that people really like that much. The ones that are, like No Man's Sky and so on, we're talking about. But the math, it's pretty interesting if you like the math and art design. Okay, so where we headed with procedural generation in gaming, nobody really, totally knows right now, but it's not going to go away. Okay, so it's definitely not going to go away. And so let's look at the math. And so what's an ellipse? Oops, let me just. ellipse. All right. Now, if we look at this, it says an ellipse is a curve that is the locus of all points. So all these points, it's like a circle. The circle is the set of all points equidistant from some center point. An ellipse is the set of all points where the sum of whose distances are R1 and R2. So that's the one red line and the other red line distances. So R1 and R2. So the distances from these foci to the point, when you add them up together, they're equal. They're equal to for all these points. So if we take the R1 and R2 for any one of these points, add them up, you're going to get the same thing. So R1 and R2 they're showing here is equal to 2 times A also. This major axis is 2A. Always across. And B, 2B is up this way. Okay, so it's like a circle. Circle really is a special kind of ellipse. And we know how important circles are in design, so ellipses, we'll see what we can get with this. And what's the generalized equation for an ellipse? Again, it's on that page. You can, oh, there it is down here. Okay, here we go, right down here. So this is the general equation. It kind of looks like a circle, right? We have like x squared plus y squared equal to 1. Or x minus h squared minus y minus k squared was the circle, general circle form. And then you got this a and b in the denominator. And that's what kind of stretches it out horizontally. Okay, the a. And then the b stretches it up and down this way. So if a and b are not equal, then it won't be circular. If a and b are equal, then it'll be a circle. Okay. All right, so who was this Gabriel Lemay? Let's take a look at Gabriel, and he kind of got this started a little bit. Gabriel Lemay, French mathematician, he contributed a theory of different things. So he was a pretty smart math guy and had this theory of elasticity and so on. And that actually some of this stuff does link into imaging and three-dimensional imaging, but it's what we're looking at right here is what he created is Lemay curves. Okay, so this right here, and why did he do this? Well, he was pretty famous, kind of smart guy, and then he was looking for some different curves, different type of curve. We had the square shape in geometry, and we had the circular shape, and then he was kind of looking for something a little bit different than the circle and the square, maybe something even in between the square. And so he started to work on that formula a little bit. And you'll notice this formula looks like the one we just talked about, the general equation of an ellipse. But you see the absolute value bars are in there instead of this thing squared. And then you see this is to the nth power. So this formula then gave a little more flexibility. So you could have not just squares, you could put higher powers in there. And we're going to go to Desmos and put in the absolute value of x divided by a. Absolute value. Okay, plus y divided by b. And I gotta get these in up here. Let's see, x to the n. And n equal to there we go. All right, so we have a and b equal to 1, and x and y, and n is at 1 right now, so we don't have, but we have something different. You notice it is a square, but it's kind of like on its side, it's a diamond shape. And if we change the 1, it takes it out that way, right? Okay. And that stretches along the x-axis then. So that's just like with the circle or the ellipse. This number stretches it right and left. And then b, that goes up and down like the y. Okay, so now, so the shape of it changes with the nth power here. So we have n equal to 1, and then as we change that, then we get a nice curve. So it's different than an ellipse or a square or whatever. So let me see, that thing will go out almost like a square, but it will have a curve on the end of it. Right? Now, if we go negative, then it'll curve inward. So we can have it concave in, right? Convex and caving in. So we picked up, and that's kind of what the whole idea was. Is it's like these people started, and this guy, like LeMay or whatever, he, you know, wanted to start looking for different shapes, some basic geometric shapes that they could start expanding what they were doing with visuals and computing. And remember, these computers, right? The stuff that they were doing, a lot of this wasn't even there yet. I mean, this, if you look, this guy, when he lived, right? This Gabriel LeMay was 17. So they weren't even, probably didn't even have much hard finding paper, didn't even have a calculator or anything. So this was all right done by hand. So the computers weren't even there yet, but they still were looking, right? This idea of looking for basic shapes that were different than just the regular basic geometric shapes, right? It has been around for a little while now. But without the computers, it's a lot of work, and it didn't seem like a lot of people had the ability to write and have paper and things up until around these later years. All right, so we have Desmos. We're going to come back to that, and let's keep moving here. So now, Piet Hein. Let's look at this guy. Okay, so you see Piet Hein a little later, 1905, 1996, right? So he's definitely was around with the computers. Now, here he was did a lot of different things: mathematician, inventor, designer, author, poet. So I guess he figured he could do just about anything. And I was looking for something. Here it is. Okay. So the Scandinavian architects, they were tired of the square buildings. They understood about the idea of circular buildings and being impractical. And they wanted Hein to help them out. They knew he was a pretty smart guy. And so he applied his math knowledge to the problem, and he proposed this idea of the super ellipse, okay, which is really what LeMay um, had developed years before, but never did anything with. So Hein, he kind of, the super ellipse became the hallmark of the modern Scandinavian architecture. He advocated the use of the super ellipse in furniture making and other realms, invented a perpetual calculator, Astro calculator, marketed housewares based on the super ellipse and its three-dimensional analog, the super egg. So if you look over here, here's that shape. If you think about 2 dimensions, so what you do is you take the shape in 2 dimensions and then you rotate it around the y-axis to create the three-dimensional rotational part of this. So it's just a super ellipse rotated about an axis, right? So calculus idea, he understood this, like some ideas of calc and so on, and then kind of became, at the time, a big interest again in architects. So Hein kept this going, and let's get this off of there. There we go. And again, so we just talked about this for what he used the super ellipse for. All right, so now, so classroom assignment 2, generate a procedure using super ellipse. So you're gonna, this is procedural generation. You're gonna write a series of steps on how to generate a design with the super ellipse and maybe some other stuff too. So um, again, uh, what I want you to see is I'm not expecting you to be able to come up with a lot of really, really great stuff, but you should be able to come up with something decent looking. You might have to go online, look around, and then we'll come back to this development here. So this is just a 2D, and if we can get Desmos back up there, yeah. So I've got this here, and I'm going to just leave that like that. And I want to make it easy for myself because I type slow. Control C. So I can put it in here. All right, so I got the same thing, and move it up a little bit. But I want to change it, so I want it to be more. Let's change these for now. I'm going to make this a C and D because I want to manipulate them independently, and M for these. Okay. Oops, Y and M. There we go. And put some new stuff. So there, I got just by default, I got a neat design. What does it look like in real life? I don't know. I'm not going to spend a lot of time on a video, but you can think how you can just take this now and play around with the adjustments. It's kind of a neat design already. I don't want to take that out. Maybe do I want to make it bigger? The outside there, or however, and then you can put other stuff in there, any things you want to make. Maybe that's a window, I don't know. And these are the drapes. But so you get the idea. Is you're going to work with the super ellipse or several, and add maybe some other stuff in it. And so then write down. So you're going to write the procedure down of how to create this. Let's say this is it. This is our design. Now I need to write the procedure. How did I do that? Of course, you're just going to basically say, you're going to write down that this is the formula that you used, and these were the parameters. A was 2, N was that. And then after you got that done, then you put this formula in, and then so you have some steps to write down on how to create this, right? Open up Desmos or its graphing package, and so on. So it's pretty simple design right now. And all right, so we got that. That's activity 2, or classroom assignment 2. All right, so let's move on. And number 16, why did John Giles create the super formula? So this was called the super ellipse. Okay, super ellipse. Super formula. So now we had people go beyond what Hein did here, Piet Hein. So we started way back with LeMay, Hein, they got it going. And now you got another guy jumping on board and saying, hey, we can even make that better. Not just an ellipse, we can have a formula that takes that and creates or allows us to create a more variety of shapes. And why did he create it? Well, he's a biologist actually, and he really wasn't concerned about architect or anything like that, or 3D imaging and all that. He wanted to be able to model things in the environment. So the biological sciences, he was looking for a way to model with computers biological shapes and so on, which really helped the development move forward. And so I have grasped the following in Desmos. This is a line. I'm not going to do these all right now. But we started with lines, and then we had circle, and then we had ellipses, and then now we got something else. We got absolute value of that. So we have the super ellipse development. Now we're jumping another. So let's see what the next progression is here. This is a major part of the super formula. Okay. Absolute value, cosine theta, taken out to x, putting in cosine theta, taking out to y, and putting in sine theta. And now r, so we're in polar coordinates. See, we had to jump ship the linear function, xy plane wasn't doing it. So now you got this in polar form, and sine and cosine gives it a bunch of up and down and in and out kind of things going on. So if we go back to Desmos, and I'm going to take this. I'll just take this first one, and I'm going to put in sine theta up. And in fact, I'm not going to do that. Cosine theta. And this one I'm going to put in sine of theta equal to r. Now you see what happened right away. Look how that changed from what we had before. We had just straight lines here. Now look, we got this nice little curvy thing going on because of the periodic nature, the circular nature of the trig function. So it was a smart way to go. And this is not the whole. I'll show you what the whole is. It just takes too long for me to type all that in. This is the foundation, but you can mess with this one. You can change And let's see. So A, it does what? Well, it goes along the x-axis out that way, right? B, not quite as much, but up and down. Yeah, you can't. It's hard, a little bit hard to see. Okay, there. And then the N really kind of makes it go a little crazy. Interesting. So it's really all right. Good. So uh, what you can do is also change this, and we could make this M, and now we got another shape. We got an M on here somewhere. Here it is, and we can get a little bit more odd, kind of different things going on. So M and N we can change. And we're not quite done, but we're done for this part of it. Okay, so I'm going to take this off. And so we're down to here. And then that kind of just led us into, so what is the super formula? What's it look like? Let's see. And here's the polar coordinates. Here's your R. Here's the cosine. And you notice they have M sub phi over 4 and sine of M sub psi over. They got these different, I used M and N. The subscripts don't, if you put them into decimals, I don't know if they work or not, but you don't need subscripts. You can just do M and N instead of M1, M2. And then this whole thing, they got this divided by 4 because it goes too fast. It slows down the circling. And then you got the 1 over this. So you can even leave this out for now. Put the rest of the stuff in, try it. You can add that in later. But here's some of the shapes that you can get out of that. So you look at the big difference, and these are just the basic ones. And then once you adjust you can keep adjusting to get other ones. But so these are a bunch. They show you the numbers that they put in for A, B, C, and D up here. Okay. And it got things going. So there's our super formula. And Paul Bork. All right, so Paul Bork. But he writes about this. There's our little bit of a different. He took this off here and he flipped the other side. So this is reciprocal 1 over. And he had the negative exponent, so he could take the reciprocal both sides of it. Paul Bork played a lot with this and came up with all these different, shapes, putting in different numbers. And he wrote the processing code to get that. And then, so you'll notice here, he even went into 3D shapes. So you see some neat kind of things here in even 3D that he created. And we'll follow up that here in a minute. So he continued to process and went even with this into 3 dimensions. Okay. Now the advancement, computer game development, and then the need to study applied math and geometry and procedural generation kind of, help advance some of the things that were going on in computing. And the most famous one came out about a year or so ago was this No Man's Sky, and you guys probably have seen this, but I don't want to talk a lot about it. There was a lot written about it, but the idea is that it was really never meant to be like an incredible game overall, as much as was, hey, here is something that we can do differently. We can use math more. In fact, supposedly, it's totally procedurally generated. and it runs on the fly, so nothing's stored. I don't know if that's totally true, but and they say that they use the super formula to do a lot of it. I think what you'll see is that they used the super formula plus more so some good coding with that, because they still had like 4 coders working on this. Uh, and I think there was a total of about 7 people, which is pretty incredible to have the game. There's a link you can look at it and see what the game looks like. It's kind of neat, and it has the qualities that procedural generation enhances. There's replayability, infinite replayability. You don't do see the same thing over and over again, but you do lack some creativity and some uniqueness and some detail, and maybe some of the fun things part of it too. But it's a really good foundation for, I think, what's to come. Now, for classroom assignment 3, so you want to generate a procedure again, just like you did back here. Generate a procedure, some steps, do a simple design, and then now a little bit more. So you're going to generate a procedure with the super formula and possibly other things to create some designs and model a simple world item. And there's examples, I showed you there. And you can use Desmos as the first part. The second part, you want to do kind of what Bork did, and then change that to 3D also. Now there's a program here, CalcPlot 3D, that'll allow you to type it in um, like Desmos. And it just runs offline. You don't have to download anything. It's pretty straightforward, but it gives you a nice 3D approach to it. So let's look over here. If you this z equal to, so this is z is a function of x and y. We want to write it in implicit, okay? So the equation now is written like what we had. So here's the equation, x squared minus y squared plus z squared. And I'm going to change that to plus. So instead of just x squared plus y squared equal to 1, this just throws the extra variable in. And let's see if this will. I was having trouble. It's kind of slow, so you got to be careful. Take this off and graph. There we go. Whoops. There it is. All right. So instead of a circle, so you get the sphere. So you're doing the same thing. Okay. And they've got, you'll see X is out this way, right? X, Y, whoops. There we go. X this way, Y, and then Z up. Oriented is your height. So you can still get circles with height, right? So what you can do is go in here then, and then just change these. You can put in absolute value around the X, like the super ellipse. You can do the super egg. You can adjust that. And again, I'm not going to type now. Again, it takes a little while to type that in correctly, so you got to be careful. But you can type the super formula in here too. You don't have to put that outer exponent in, and you can still get some neat designs. So one place you can look for some functions and so on, and you can play around with this. It's a neat little program. It's really is good for plotting 3D. This is like the best, easiest one to use out there. But what you might want to do too is, again, you can play around with this, but I want to go to the last one and then come back. But for classroom assignment 4, you're going to do kind of the same thing, except it's going to be actually a little bit easier. It'll be a little bit funner because, here's a guy that extended it further. He took two super formulas and created a cross product and came up with a nice formula for, so it's a system of equations for the super formula in 3D. So Andrew Marsh uh, has a great app. Let's see if we can get it up here. But it's the super shapes, basically, because it's 3D super formula. So this isn't, you can't play with this one. Just click on launch the app. There we go. And this will give you random, it'll generate things randomly. But you can go to the shape settings, and here's the super ellipse, the super formula. I'm going to take the spherical harmonics off. I want the super formula. There we go. All right. So pretty neat. And how are they getting this? Well, you have the super formula, and you have to look over here at what they're putting in for the exponents. I got 5 for the longitudinal is the up and down, and that's the y. And then the exponent, the latitudinal frequencies, again, are going this way, going up. Should be. Let's check it. Let me see if this is gonna. Yeah, let's just go in and out. Oops. That's doing nothing. Oh, okay, that one fell apart. So you're just gonna have to play around with it and see if you can come up with something kind of neat. But a whole lot different than just working with the cubes, cones, cylinders, and then piece them together. So yeah, and again, you can kind of play around, and I haven't played with this too much, but you can random if you want to reset to something else. You can start with something and reset it. And the load settings, again, I haven't had a chance. You guys, just have some fun with it and see what kind of shapes you can create. But that's really about it. And if you have any questions, again, just email me. If not, again, we have this next week is a lab, so we can get online and talk about it and hopefully answer some questions then. And then the following week will be in activity 7. So we still have a lab next week and see what you can get done. All right, we'll see you guys on Wednesday.